This section is about the various noise components that are generated inside the op-amp. There are two types of noise sources, a current noise source and a voltage noise source. These two noise sources are added to the now familiar op-amp. The current noise sources are connected in series with each of the input terminals. The voltage noise source is connected in parallel across the same input terminals. Keep in mind that the many op-amp applications require the amplification of signals in the nano and microvolt range. The op-amp noise sources produce noise signals in the nanovolt range. This will contaminate signals in the nanovolt range. So in applications where low signal amplification is required, the op-amp noise figures must be taken into account. So, an understanding of the modeling and specification of these noise sources is necessary, and is covered in this section. This clip is taken from the datasheet of an op-amp. It shows the specification of the input referred voltage and current noise sources. Note that the units are quite complicated and require some explanation. Also note that the noise figures are specified as specific frequencies. In this example it is specified at 100 kHz and 1 kHz. The noise figures are expressed as nanovolt and picoamp per the square root of kilohertz. These noise figures are known as the noise spectral density, because they are dependent on frequency. This is what the spectral noise density typically looks. In general, it starts off high at the low frequencies, and reduces as the frequency increases, until it reaches the corner frequency. After the corner frequency there is just white noise, meaning the noise stays constant and does not vary with frequency. The corner frequency is a figure of merit for an op-amp noise performance. Lower corner frequencies are better. Low noise amplifiers have corner frequencies in the range of 1 to 10 Hz. JFET devices and more general purpose op-amps have values in the range of 100 Hz. Very fast amplifiers have quite poor corner frequencies in the region of 1 to 2 kHz. The voltage noise and the current noise do not necessarily have the same corner frequency. In this slide, we introduce the op-amp noise specifications and we use a specific op-amp example. Let's use the OP27 as an example. This is an analog device's op-amp. The voltage noise is 3 nanovolt per square root hertz. This is a low voltage noise figure. The current noise is 1 picoamp per root hertz. This is a high noise figure. Let's assume that the op-amp is used in a non-inverting amplifier configuration. The voltage noise generated by the output resistance of the source is shown here as 7 nanovolt per square root hertz. This is the non-inverting amplifier with an OP27 op-amp. The voltage and current noise figures are shown in the top left. Note that these are specified at a temperature of 25 degrees Celsius. So we expect that these noise figures are temperature dependent, and will change with temperature. The noise contribution by R1 and R2 is neglected. The source resistance is indicated here. This is resistance with the voltage noise of 7 nanovolt per square hertz. With zero source impedance, the voltage noise will dominate as shown in the left column of the table. With a source resistance of 3 kΩ shown in the center column, the current noise of 1 picoamp per square root hertz flowing in 3 kΩ will equal the voltage noise, but the Johnson noise of the 3 kΩ resistor is 7 nanovolt per hertz and is dominant. With a source resistance of 300 ohms, shown in the right column, the current noise portion increases 100-fold, to 300 nanovolt per square root hertz, voltage noise continues unchanged, and the Johnson noise of the resistor, which is proportional to the resistance square root, increases tenfold. Overall current noise dominates. Low impedance circuits use low voltage noise amplifiers. High impedance circuit use low current noise amplifiers. Bipolar junction transistors tend to have lower voltage noise than JFET. Low noise JFET op-amps have larger devices and therefore higher input capacitance. This is the end of the short section on the op-amp noise. There is more to op-amp noise, but the information supplied provides the student with a basic understanding of the two types of op-amp noise, and how to evaluate figure of merit. The corner frequency, lower is better. The next section is about the gain bandwidth product.